Hello, everyone. Welcome to today's ARMA Future Leader webinar. Today's speaker, kindly joining us from Tongji University in China, is Dr. Haitao, who's a tenured professor in civil engineering. He received his PhD in tunneling and underground engineering from Tongji University and studied geotechnical engineering at Purdue University from 2009 to 2010. Dr. Yu's research focuses on seismic design and analysis of underground structures and seeking solutions, whether analytical, numerical, or physical, to these problems. Dr. Yu has received a number of talent awards, such as the Outstanding Young Scientist Award from ICDGR, the Excellent Young Scientist Award in 2019 from NSFC, and the Shanghai Youth Scientist Talent Award in 2020. So with that, thank you so much for joining us, Dr. Yu. The floor is yours. Look forward to hearing about your work.
Okay, thank you, Bing. And good morning, and good afternoon, and good evening, everyone. I'm Haitao Yu from Tongji University. First, I would like to thank Bing and Wei for organizing, this ARMA Future Leader webinar. And it's my great honor to take this opportunity to share with you my recent progress on seismic facts and mitigation control for channels. So as I said before, I will try to keep the presentation within 40 minutes. Then we can leave some time for discussion and question and answer. So here's the outline of my presentation. First, I will give the brief introduction of the background and motivations of my research. And then I would like to show you several seismic analysis methods for the tunnel structures, where especially focus on the longitudinal response. And also based on this method, so we can, obtain the meaningful data, and then we can give a full understanding of the seismic effect on the tunnel structures. And also based on with this knowledge, we can propose seismic mitigation control technologies for the tunnel structures, including the shield tunnels and the immersed tunnels. And finally, I would like to end with conclusion. So as we know, the underground constructions are booming recently, especially in China. For example, there are a number of submarine tunnels distributed in the eastern coastal areas of China. And also we have a large number of mountain tunnels in western areas of China. But during recent earthquake, like in 2008 Wenchuan earthquake with a magnitude of 8, so we have investigated 55 mountain tunnels close to the epicenter. So we found that 38 of them were damaged in different levels, including the cracking, concrete spalling, and even the collapse of the whole tunnel liner. So which bring the evidence that the seismic design for tunnel structure is still an important issue, which we're not understood yet. So from the literature review, current studies on seismic analysis of tunnel structures focus on the 2D conditions on the cross-section response. That is, assume the problem as the 2D plane strain condition and only consider the shear deformation of the tunnel section under vertical shear loads. But there's still other two deformation along the tunnel. One is called warming deformation. We call the tunnel have the axial compression and extension. Another called the snacking. We call the tunnel have the longitudinal bending deformation. So actually, this deformation mode was already reported by Owen in 1981. And also, from this view, the tunnels have long distance, and so for earthquake, when traveling at if each section of the tunnel, maybe the time lag is different due to the wave passage effect. Another issue is that the tunnel, crossing different soil mediums with different soil stiffness. So that's where cause the non-uniform sun input along the tunnel. But currently, a few studies have been reported on such field. So that's the focus of my research. So to understanding, the longitudinal response of tunnel structures and the non-uniform sun input, so we better propose several the seismic analysis method. Well, we can use, the current on-site seismic monitoring, we can use to understanding the seismic effects of the site. But, it's hard to use for the understanding of the soil structure interaction under the seismic loading, because we don't know when the earthquake will come and how it come and where will it come, where is it. So one of the physical model test will be one of the options, to use to understand the turn response under the different under seismic loadings. So even we currently we have the advanced facilities like in Tongji, we have the 4 large shaking tables which can removable in a long trench with a total length of 70 meters. But actually, this facility was developed for the bridge engineering because for each bridge pair we can put on one shaking tables. So then we can do the same put on different shaking table to realize the non-uniform, the discrete uniform sand input. But the critical issue for simulation of non-uniform sand input for long tunnels is that how can we use 4 discrete shaking tables to realize the continuous sand input from the bedrock? So to solve issues, so first we propose the test theory that we have to develop the model container to transfer the sand input from the shaking tables into the bedrock. So first, we can assume the model container as a beam. Then we can obtain analytical solutions for the beam response under continuous sand input and the discrete sand input. Then we can obtain the analytical relations, from the theoretical views. And with this, we can also obtain the analytical solution for design parameters of the model container. So here's slide shows the equation. The B actually is the distance between each 2 adjacent shaking tables. And you can see this is related, the value is related to the not only the physical parameters of the model container, but also the wave properties like the circular frequency and the wave velocity. So with this design parameters, we can realize, this continuous sand input from the discrete seismic from the discrete shaking tables, but only from the theoretical view. But if we can, realize such design parameters. So with this theory, we makes a model container, so which consists of segmented boxes and the connections between each of them, and also the supporting system to keep the model container can move in the horizontally, and also there's with no frictions between the supporting system and the model container by using the ball joint. So the total length of the model container is 40 meters, and the width is 4.5 meters, and the height is 1.5 meters. So when this facility is done, we do a number of validation tests, including not only the vacant continuum, vacant model container, but also the free field test. So we can see that the acceleration from the bedrock at the bottom of the model container. So in either the transfer directions or longitudinal direction are consistent. The test data are consistent with that of the theoretical value. So and the errors for the phase angle, wave patch effect can be neglected. So which first demonstrate that the developed model container can well capture the wave patch effect, from one side to another. So with this facility, we actually applied to several projects in China. Here is one a super long immersed tunnel with total length of 6 kilometers, which is the world's longest immersed tunnel in the world, and to connect 3 cities, Hong Kong, Zhuhai, and Macau. So we put the whole tunnel, in the model container to want to simulate the non-uniform sand input on the turn response. And for the geometric square ratio is 1 to 60. And for the model soil was a mixture of sand and sawdust. And also for the model tunnel is made of aluminum. And also we further consider the immersion joint configurations were based on the equivalence of joint stiffness principle. So with this developed established shaking table test, we do a number of shaking table test cases, including not only the uniform, non-uniform sand input, and also with different seismic waves, seismic input intensity levels, and also different directions. So we obtained from a result that compared with the uniform sand input, and the non-uniform sand excitation would significantly amplify the turn response. For example, for the immersion joint deformation, so it will be amplified to over 3 to 5 times compared to that of the uniform sand input. So which means we should be pay more attention for the seismic design of long-term structures. So since the physical model test, they still have some limitation. Like first is the skilled ratios, and also second is very expensive, and we cannot do many test cases, and also the test data is very limited due to the limited sensor we put in the model test. So the numeric simulation would be another option to better understand the soil structure interaction under different seismic loadings. So but the tunnels, long tunnels, you already have the distance over the kilometer grid, but for damaged areas, you already focus on the critical sections or joint. So in the millimeter scale, so from the kilometer to millimeter, the multi-scale do exist for the numeric simulation. So we can use different models and the different meshes, to consider different scales. But the critical issue for dynamic problem is that the spill width wave reflection will occur at the interface between different models and different meshes, so which was already addressed by Professor Ben Shekro from Northwestern University in the US, who was passed away a couple of years ago. So based on the branch domain method, we proposed the Musco method by coupling the different meshes. Like the coarse mesh, we can simulate the equivalent the tunnel structure without joint. But also for the refined area, we can simulate more in details about the segment and joint and both the configurations. So to connect each two scales, first we set overlapping areas between each models, and then we can introduce parameter alpha. It's from 0 to 1 to give a linear combination of the energy between coarse and refined meshes in the overlapping areas, so we can obtain the total energy for the whole domain. Then we also further consider the constraints between each two models at the overlapping areas, and we consider it into the total energy by using the multiplier Lagrange multipliers. So with this, we can obtain the Gaussian equations for different scales. So because this method is based on the energy, so the proposed method does not have spurious wave reflection at the interface, and also does not need any artificial filtering procedures. So we can use to solve this equation, we can use the central difference method, which is explicit algorithms. But if we use a single time step, but the computation cost will be very expensive, especially when the number of coarse meshes is much larger than that of refined meshes. So we further proposed the hybrid time step algorithm. That means for different scales, we use the different time steps. Then we update the velocity and the displacement at the overlapping areas. And we also do comparative test as for a model with total mesh of 3 milli. So we run the model using single time stamp and multi time stamp. We found that the computed efficiency can be significantly improved to over 8 times compared to that of the single time step. But the computation accuracy was consistent with the single time step algorithm. So to further consider the damage of the tunnel structures and under strong earthquakes, so we further extended the Musco model by coupling continuous domains using the finite difference method, and with the discrete domains to simulate the cracking or spalling or collapse of tunnel by using the discrete element method. And also similarly, we use the Musco model to connect the two models to ensure that the wave can transfer smoothly from one model to another across in the overlapping areas. So which we also do several case studies to validate the accuracy of the model. So with this method, we have applied to also several projects in China. Here is a super long water conveyance tunnel with a total length of 14 kilometers, was built in Shanghai at the shield tunnel, built in soft soils. So we use the Musco models to simulate the whole tunnel and soil system. And also we can see there's dimension of the model, and there's the length, and the second is the width of the model is the 2.5 kilometer, and the total depth of the soil layer is 300 meters. So the total element mesh is almost 4 million. So we used we do the simulation in the Shanghai Supercomputer Center using 65 CPUs, and each one takes around 3 days to finish. So with different case studies, we obtained many meaningful data. And with that, so we can better understanding the turn response under different standard loadings and with different bear depths and crossing different soil mediums. So, well, since the numerical simulation and the physical test, is still complicated for the design. For practitioners, they much love the analytical approaches of pseudo-static analysis because it's very simple and easy for calculation. So based on the understanding of the result analysis from the numerical simulation and the physical model test, so we can assume the long term as a B model because the cross-section dimension can be negligible compared to the longitudinal length. So for the surrounding soils, we can assume as the elastic or viscoelastic foundations. And also for the dynamic loads, like the moving train, we can assume as a moving land load. And for the construction load, can be assumed as an impulsive load. And for the wave passage effect, can be assumed as a traveling load we put on the tunnel structure in the longitudinal direction. So first, we obtain an solution for the Euler Bernoulli beam resting on a vertical wind curve foundation subjected to the arbitrary dynamic loads. So you can see from the picture that the EI is a bending stiffness of the beam, and rho A is the mass, and also the F is the arbitrary dynamic loads can be distributed along the tunnel length, and also K is the soil spring stiffness, and C is the damping of the soil. So we can inside the communications for dynamic problems. It's very simple. So for the first atom in the left side of the equation is corresponding to the internal force. The second one is the initial force, and last two atoms correspond to the reaction from the soil foundation. And the atoms in the right side of the equation corresponding to the arbitrary dynamic loads. So we further consider the initial conditions as static, and for the boundary conditions, infinite long for both ends of the beam. So we can employ the integration transform method. That is the Fourier transform method in the space domain and Laplace transform in the time domain. Then we can transfer the original partial differential equation into the algebraic one. Then we can, use the inversion to get back to the original space and time domains. We further use the convolution and the retention theorem to further simplify the expression of the solution. And here we give the final generic express solutions for the deflection response of the beam. And we can see that if the form for the dynamic loads is specified, then we can obtain the degree solutions. So we later expand the Winker foundation to the Pastner foundation to further consider the shear deformation of the continuous soil layers. So we can see we added a new atoms corresponding to the shear modulus of the soil into the equation. Then similarly, we can use the integration transfer method to obtain the analytical solution. So the right part of the slide shows the parametric analysis on the shear modulus of the soil. So you can see GP is 0 as corresponding to the Winker foundation. And the GP is from small to large is corresponding to the practical conditions of the soft soils and the hard rocks. So we can see that the dashed line, the black solid line is GP to 0. So you can see it gives the largest responses of the beam structure. So, which means that the Winker foundation will give a conservative prediction. So later we extend the Euler Bernoulli beam to modified temperature beam by not only consider the shear deformation of the cross section, but also the rotor inertia caused by the shear deformation. So we can obtain two common equations for force and bending moment. Then similarly, based on the integration transfer method, we can obtain the two unknown atoms is deflection and the bending rotation angle of the beam. So then we can, with this solution, we can, do parametric analysis for the different kinds of dynamic loads and with different frequency. So we also extend the original infinite uniform beam to the finite uniform beam because, for the short channel with limited length, so we may be able to have to consider the conditions on both ends. And also the tunnel may crossing different soil mediums with different stiffness. So here we use the model superposition method to obtain another solution. And also we expand the original straight beam to the curved beam. We want to consider, the curvature of the tunnel structures in both the vertical and the horizontal plane. So similarly, we use the model superparameter method to compute the solution. And with this solution, we can do parametric analysis on the influence of curvature of the Turner structure on the structure response. So here I give the unified solution, for the longitudinal response of the long channels. It includes not only the the long line channels, the curved channels, and the traveling loads, but also the channel buried in late ground and the inclined waves, and also long channel with shaft stimulated transition across the different soil mediums like soil and rock, and also the shallow buried the channels affected by the relay waves. So here I want to give several case studies. So case one is the application of analytic solution, to a subway tunnel in Shanghai in soft soil, which was built by shear tunnel. We want to consider the dynamic response of the tunnel structure under the traveling loads. So you can see here's the the plot shows the typical cross-section dimension of the subway tunnel in Shanghai. And also for the wave passage load, we can give the specific expression that the P is amplitude, omega is the circular frequency, and the V is wave traveling loads. So assuming there's no damping, so we can obtain the deflection of the beam response under the traveling loads. So, but there's one issue is that, for shear tunnel, it have the circumferential joints and the longitudinal joints. So how can we assume, this discrete structure into a uniform beam? So here we obtain a next solution for longitudinal bending stiffness for shear channels. Well, by not only consider the details of the circumferential joint configuration, including the rubber gasket, bolts, and segment, but also consider the transverse stiffness of the tunnel structure by considering the deformation as the overhang deformation, and we introduced the two parameters A and B, of the overhang deformation into the expression. So with this analytical solution, we can obtain equivalent unified stiffness for the beam structure by considering the details of the joint configurations. So then we can obtain the solution, and with solution we can do many parametric analysis. So this slide shows the parametric analysis on the wave velocity. So you can see it's a moment and the shear force response of the tunnel structure under uniform loads and traveling loads. Well, for the traveling loads with a velocity of 200 meter per second, so which is corresponding to the soft soil, and also for the uniform loads is corresponding to the velocity with infinite value. So we can see the black dashed line is the traveling loads. We can see the solid red line is the uniform load. We can see that the wave passage effect would significantly amplify the turn response, and which should be paying more attention in the seismic design of long-term structures. So we can also do parametric analysis on the influence of wave velocity and the frequency. And so we can see both of them have dramatic effect on the turn responses. And what's more interesting is that, for the beam response, the moment response, for the wave passage velocity is from the 200 meter per second to the 800 meter per second. The response, the beam response first increased and then decreased. So that means there's a critical wave velocity exist for the seismic design of the turn structure. And from the frequency response, we can see the lower frequency give the large response. That means we should be paying more attention for the turn structure buried in soft soil, because for soft soil, the frequency will be much lower than that of structure buried in the rock. So case two is the application of analytic solution, to a long channel with sharp standard transition. So you can see tunnel 1 and tunnel 2 is buried in different soil medium, and tunnel 3 is a transition tunnel to connect each tunnels. So first we'll give the simple model like here, and also we assume the free field deformation was simplified as harmonic waves, and we want to further consider response, at different sessions. We move the harmonic load along the tunnel with different phase angles. So then we can obtain a pseudostatic analytic solution for the beam response under different phase angles. So with this analytic solution, you can apply to real project in China. It's a number 3 metro line in Xiamen. So tunnel 1 is a rock tunnel built by the mining method, And tunnel 2 is a soft soil tunnel built by the shield tunnel. So tunnel 3 is a transition tunnel, connect tunnel 1 and tunnel 2. So we can see the bottom of the slide shows the bending moment and shear force response of the tunnel structure along the tunnel direction. So we can see that the sudden change of cross-section and ground property here with the dashed line will lead to a significant internal forces in the transition areas. So we can, with our developed analytical solution, we can easily to give the design, to obtain the given evaluation of the safety of the structure. And also with this solution, we can also do parametric analysis to give the optimal design parameters for the tunnel structures, especially for the transition tunnels, crossing the soil mediums with shaft stability transition. So with this developed method, we can to better understand the soil structure interaction behaviors, and also we can give the seismic effect observation for the tunnel structures. So as I mentioned before, this slide shows the tunnel response on different directions. So we can divide it into two parts. Part one is the cross-section response under the uniform seismic input, and another is the longitudinal response under the non-uniform seismic input. So as we know, for the sectional cross-section response of the tunnel structure, there's a lot number of literature review. But what I want to show you is that we developed a unified solution for transverse response of underground structure, because from literature review, so most studies focus for the circular or rectangular with specified shape, but here we obtain a unified solution for tunnel structure with arbitrary linear sections, which is very important for mountain tunnels, because for mountain tunnels the shape is we have different kinds of circular regions of different arch areas. So also we consider different the tunnel barrier in different ground conditions, including the isotropic for the rock, and those saturated conditions with drained and undrained conditions, and also for the soil structure interaction, including the full slip, no slip, but also consider the voids behind the liner. It's due to the construction issues. So the proper unified solution can be very suitable for the arbitrary cross-section tunnels and also buried in the different ground conditions. So for the cross-section response, what I want to talk here is that because from current studies or current design for tunnel structure, they only focus on the structure safety, but they neglect the inner structures, the non-structure components, and also the function of the tunnel structure. Like here an example. So here's the road tunnel built in Shanghai's Zhuguang road tunnel with lot diameter of 40 meter and 1.4 meter long. So this tunnel has had 4-lane system with double leg, 2 lanes for top and 2 lanes for bottom. And outliner is a shield tunnel. For inner structures is also a prefabricated structures. It's similar. We say that this structure like we build a bridge inside of a tunnel. Yeah, like this. So for the current design, they only consider the outliners, neglect the inner structure. So how about the influence, of the inner structures and also the interaction of each two outliner and inner structures? So we do the comparative test. The first slide in the first one is the segmental liners without the inner structure. So this is the current design. And second one is the double deck system. It's corresponding to the practical condition. And the last two is just for interest, the full ring and the semi-ring with at the bottom, just for the reinforcement of the structure. So what I want to show we've obtained from the comparative cumulative test under the harmonic loads. So we see that it's very interesting for the tunnel structure without inner structures. So we can see the tunnel have the very smooth overlay deformation. It's very well known, it's due to the pure shear deformation. But for the tunnel structure, consider the inner structures. So we see that the liner response first, this decreased in the lower half of the tunnel because due to the constraint of the inner structures, but it will increase in the upper half of the tunnel structures. And also the connection of the inner and the outer liners will significantly amplified, compared with that of the structure without the inner structure, the tunnel liner without inner structures. So this, of course, this response is related to the stiffness ratio between the inner structures and outer structures, and also the connection between each of them, and also related to the sediment weave properties. So which with this test, so we better understand the connections, between the inner structure and outer structure, which should be pay more attention for the sediment design of practical engineering. So for the longitudinal response, I do not want to take too much time to share, because I will already show you in the previous sessions for the Shingative test. So we use Shingative test to invest the dynamic response of super long immersed tunnel connect Hong Kong to Haimaco, and which is also located in the high seismic intensity areas. So from the test result, we see that for the tunnel structure response both in longitudinal and transverse directions. So we also compared it. The response is amplified compared to that of the uniform sand input. And also we use this facility to investigate the long ship channels in Shanghai under the non-uniform sand input. Also, we see the bottom of the animations shows the response under uniform and non-uniform sand input. We can see that under the uniform sand input, the tunnel response, they move in the same direction. That symbolize like a state structure movement. But for the non-uniform sand input, the tunnel will have a very S-wave, S-shaped snacking deformation, so which will enlarge the joint deformation of the tunnel. So which should be pay more attention for the practical design. So what I want to show here is we call the third one is the space effect, which is due to the tunnel structure stiffness transition, and also maybe due to the tunnels crossing different soil mediums with different stiffness. So here, first one is the junction with the shaft transition of stiffness, like the shear tunnel connect with the working shaft and or work cross passage. So the connections between like the tunnel and the shaft, we obtained from the Shingative test that the joint deformation at the connection will be amplified up to 10 times compared to the norm areas far from the connection. So it's very significant. So we put it to the design. We also further to propose several design measures to consider this situation. So another one is subway station. Is Shanghai. It's built across the already existing bridge, highway bridge. So we use the combat station construction that for each side of the bridge we built using the cut cover, and for the crossing areas we use the pipe jacking. Clearly, the connection of this, at these pipe jacking covers will have a large response due to the stiffness transition of structure. So this another one is that subway station built in rock in Qingdao. So we built the substation using a grouped tunnel. Like for top tunnel is built for the station hall, and two bottom for the station platform. And also we built several passages to connect each of them. So similarly, we do the Shingative test and numeric simulation to observe how is the effect of the tunnel group and how its mechanisms. So clearly the space effect to exist. And there's another one is cross transfer substation. So which is very common in metro cities, and for the subway transfer system. So we also do from Shingative test to see how it affects and the connection of this at the cross transfer subway station will very significant. So if we do the current design, we do the this way and that way, we just do the cross-section response, we cannot get the connection response because there exists a space effect at the connection. So we obtained a mechanism and also developed several design methods, simplified design methods for the practical design. So there's another one is for the soil stiffness transition. So here's the road tunnel built in Nanjing. Actually, it's across the soil and the rock. So we observed from test that the tunnel, at the interface of soil and rock have a large response. Of course, due to the difference between the ground deformation in soil and rock. Yeah. So there's another one is shallow buried tunnel structure in Shanghai. Actually, is a shell tunnel without working shaft. So for deep, it's very interesting that for deep buried shell structures, it's controlled by the ground deformation and soil structure interaction. But for the shallow or even the structure above the surface, so it's controlled by the initial force of the structure itself. So how about between? How about between these two areas? That means the critical depths should be considered for the seismic design of this kind of structure. So actually, this is the dissertation of my one of my PhD student. So another one is that actually subway near Valley subway station, so which was planned is the first subway station planned in Makati, Philippines, because you know Philippines is the high seismicity areas crossing the fault. So in this case is that the subway station with shallow buried depths and close to the water valley. It's the closest distance, I think, is 7 meters. So we do a number of sequential tests to investigate the topographic effect on the shallow buried near subway stations. So there's another one is a subway station structure with the diaphragm wall. You know, actually, for the practical designs, some design companies only consider the inner structure and neglecting the effect of diaphragm wall. So if it's safe or not safe, so we do a comparative test. We both consider subway station with and without diaphragm. We put in one mold container and put on Shingley table. So we see from test result is very interesting that, you know, for the subway station structure, consider the diaphragm wall. Of course, the deformation of the subway station will be reduced due to the constraint effect of the diaphragm wall. But meanwhile, it will bring much more dynamic soil pressure on the diaphragm wall. And especially, you know, for the connection between the station bottoms and the diaphragm wall will have the large response. So which should be paying more attention for the practical design of this structure. And currently we also developed some, you know, simplified analytic solution to consider the effect, the adverse effect of the diaphragm wall. So with this understanding of the seismic effect on the tunnel structure, so we can better propose the several seismic mitigation control technologies want to further, you know, improve the seismic performance of the tunnel structure. So first one is the cross-section response. You know, it's well known that the tunnel cross-section response is controlled by the stiffness ratio between the soil and the structure. So maybe we can, you know, put a cover the tunnel with the isolation coating layer. But how can we design the parameters? So here we obtain another solution for the tunnel covered by isolation coating layer. So with this solution, we can do parametrics to give optimal design parameters for the coating layer buried in of the structure, buried in different soil mediums. So it's very interesting that, you know, for the tunnel structure buried in the soft soil, so the coating layer should be much stiff. It's like we do the growing effect. But for the rock tunnel, the coating layer should be very soft. So for the shell tunnel, you know, the seismic performance for shell tunnels is comparatively very good because it's very flexible and it can be well adapted to the ground deformation. But what I want to focus is the connection between shell tunnel and working shaft. As I mentioned before, the connection will be responsive at the connection will be amplified up to 8-10 times compared to normal areas. So we invite a seismic mitigation configuration and inserted a connection for the circumferential joint. So we observed from the skin tip test that with this facility, with these measures, so the maximum tension stress of tunnel structure can be reduced up to, you know, 20%. Well, for the immersed tunnel, you know, we take example for the Hong Kong-Zhuhai macro linkage. If for each element of the immersed tunnel is about the length is about 180 meters. So if we take this model with integral tab, there's uniform, you know, the element is uniform without any joint or circumferential joint. So we observed from the numerical and the physical test that more than 80% of the joint opening will over the limit. That means that the joint leakage will occur. So we proposed optimize the segmental method for immersed tunnels to want to separate the integral tab into 8 segments. to better adapt the ground deformation as part of the seismic space effect, along the tunnel. So we observed from the numerical and the physical model test that the joint opening will be reduced up to 70%, and all of them are without exceeding the limit. So which effectively supports the construction of immersion of Hongzhou-Zhuhai macro linkage. So since the immersion joint, is a weak part compared to the stiffness of the segment or element. So we further invent a novel seismic mitigation joint, which is replaceable buckling restraint brace, damping components, which for each we put on each side of the sidewall of the immersed tunnel. And we do large scale, it's 1 to 10, with the geometrical ratio is 1 to 10. We do a structure test for the immersion joint. So we observed from test results that the energy dissipation capacity of the joint is increased up to 7%, and with this developed the equipment, and which further guarantees the structure safety and strong earthquakes. So here I would like to end with conclusion. So we propose several analysis methods, the physical, numerical, and analytical method, to better understanding the tunnel response, source strong interaction, and also the damage mechanism of the tunnel and the strong non-uniform seismic input. And with the knowledge of the behavior, so we can better propose seismic mitigation control method, and to want to give the resilience design, and they want to increase the seismic performance of the tunnel structure. So we also applied this method, the seismic mitigation and also the analytic solution to a number of projects, not only in China, but also in Philippines and other overseas areas with strong seismic intensity requirement. And also we input the method and technology involved in 5 national, industry, and local standards in China. And currently, actually, I'm the vice animator of the seismic group 9 in the International Tunnel Association. Currently, I want leading the first international standard for tunnel seismic resilience design. So here's my contact information, and following our published review paper for your reference. And also this work, of course, I contributed by my research group, and much appreciation goes to my research group. So final one is advertisement. So currently I'm the guest editor of the spare issue in tunneling and underground space technology, which is focused on seismic disaster prevention and structural resilience of underground infrastructures. So I co-edited with Professor Peter Lex, Yanis, Rohr, Emilio, Janina, and Ahmad. So this submission was already open and will be closed in the end of this year. So welcome for your submission. And thank you for your attention.
Excellent. Thank you so much for this talk. This is a tremendous amount of work incorporating the whole range of scales, which is really cool to see. So thank you so much. And congratulations to you on this tremendous body of work.
Yeah, thank you. I hope his time is okay.
No, time is great. Time is great. We have plenty of time for questions. So if anyone in the audience wanted to ask, please feel free to unmute yourself, or you can leave a question in the chat, and we can read it out for you. Questions from the audience? I can start with one if people are shy.
Yeah.
So you talked about how you coupled a discrete element model to a finite element model near the beginning.
Yeah.
Could you talk more about how this coupling is done? Because that's very curious.
Okay. So so let me see. Can like this slide, right? So can you see that here?
Yeah, I can see your slide.
Yeah. So actually, this connection, is based on the bridge domain method. And actually in this method, usually we can first set the overlapping areas, like for the coast domain and the refine domains. So I see here is the inside here is the refine domain. The other is the side is the coast domain. So we put the overlapping areas like a bridge, like a bridge.
Yep.
And so to consider here, first, we introduced the parameter alpha. It's from 0 to 1. Want to connect the energy in refined domains and coarse domains, give a linear combination at the overlapping areas. So we can want to turn the energy can be transferred smoothly over these areas. But also there's another thing is that there's constraint equations, in the overlapping areas, like for the mesh, for the finite element mesh in coarse domain and finite mesh in the element node in coarse domain and refined domain. This should be satisfied by the constraint equation for displacement. So we put this equation into the total energy by using the Lagrange multiplier method. To consider is that like no constraint problems. Then with this is established the total energy, so we can obtain the Gaussian equations, for the coarse domain and the refined domain. Like here, here is the equation. It's a very simple equation. What the difference is that the last atom on the right side of equation is corresponding to the Lagrange multiplier, which is constraint equations, which is also an unknown atoms, which should be solved. So we use this central difference method. First, we didn't consider the constraint and give the trade velocity, and then we further consider the velocity balance equation at the overlapping areas. Then we can obtain the equations for the equation to solve the Lagrange multiplier. Then we update it to get the true velocity. So for each time step, we can do the iteration, to until the final time was solved. So this is the whole procedure. And also later we expand this to this one. It's similar procedure, but different. The original one is the mesh, the finite mesh with the coarse and refined. But here is the for the finite difference method and the discrete method. Similar. We do the similar way. We use the bridge domain method, to connect them.
Very cool. This is really cool. And it's rare to see people coupling things this way. It's cool.
Yeah. Thank you.
Other questions from the audience? Please don't be shy. Oh, yep. So,
I see one.
So hello, Professor Yu. May I ask if there is a comparison between simulation or experimental results and measured data or post-earthquake tunnel damage? So was there, I guess, there's a field comparison.
Actually, we do have the comparison, but for the due to the limited time, didn't mention here, I separate this method, the numerical, analytical, experimental. So I separate. But for example, for the numerical simulation here, as I mentioned here, we also do the but this test is a validation test. You really focus on on this like here. For this validation test, it's hard. Usually we can only do do the local areas, but for the whole engineering here, it's difficult. But for the physical test, yes, usually when we do the physical modeling, first we will do the numerical simulation. But this numerical simulation is just in the same scale with the test. And first we use the numerical simulation to get how we can design the test. And with the test data, we can go back to validate the numerical model and to compare it. Well, after this comparison, then we use the numerical model to get back to the original scale, using scale ratio. So for the validation, only focus on this same scale with the physical model. So that's the validation, for the numerical and physical test. And actually, for the field data, it's very limited because you don't know when earthquake will come. That's the difficulty. We don't know. Actually, currently we have some projects. They also pay more attention. So we maybe give some suggestion. You can put some monitoring sessions at here, especially in the earthquake areas with frequent happen earthquakes. So then we can to get the data to further to evaluate the design the design scheme. So but currently I think no, because you don't know when it will come. No, no different, no different. Currently, yeah.
Yeah.
You're just a numerical simulation, the physical, yeah, kind of this, yeah.
Well, no, just the scale of your shaking table test is impressive, right? I see a person for scale. This thing is what, 100 meters long, 50 meters long?
You mean this one?
Yeah, the model, the
Yeah.
physical.
The physical model, we put in different scales. Like because this like Hong-Zhuhan macro linkage, it's very long.
Yeah.
So
Yeah.
we do the scale ratio to 1 to 60. So it's kind of quite small. But later when we do the other model test, like here, this one, and also like in this one. So this one, the scale ratio is I think it's 1 to 10, 1 to 10, or 1 to 15, 1 to 15. It's very large. So we put two shingle table together. So the dimension can be 10 meters multiplied by 6 meters. So it's very large. So the diameters is almost 70 centimeter. So the person can go inside the place the sensors.
I hope not during the shaking.
No, definitely not. That's so dangerous. No, they will kill us. No. But there's still some issues. It's not very good that see the people we do here. And it's not, some people we take the hat, but
This guy's not wearing a helmet. Oh,
okay. Now we have the most strict. Now we have the most strict restriction. I think
good to hear.
then it would be fair, I guess. Yeah.
Okay. Glad to hear that. Other questions from the audience? Again, please don't be shy. Okay. If not anything else, then thank you so much, Dr. Yu, for your presentation. And best of luck in your...
Thank you for your organization.
Not at all.